coming. We have about 55 slides to go, and we got about 40 more minutes to do it. So we're going to go really quickly. Let me just first introduce myself and my co-presenter. I'm Konrad Wilk. I work at Oracle. I manage and direct the Xen and KVM virtualization product. We're working on both sides of virtualization. And today I'm happy to present a presentation about QEMU and how to slim it down, along with Marc. Marc, do you want to introduce yourself?
So my name is Marc-Andre. I work for Red Hat for the past 7 years, and I've been working on QEMU for the past 2 years.
All right. So, by the way, if you have questions, just raise your hand, wave. We'll try to stop and answer them. But also, we have time afterwards, so you can always come and ask us. And one of the things that's kind of neat is, I'll go really quickly in some of these slides, is QEMU, when it started, was a really cool project. You could use it to test different things. You can still use it, obviously, with the translator. You can run on x86. You can run Arch64, ARM code, and build it, and so forth. But it is used in virtualization for both KVM and Xen. There's different ways it's used. And I figured at the beginning of the slides, I'm just going to give you guys an overview of how it's used in one world, and then we're going to jump to the other world and how we can act, what we both were thinking of going forward, and looking forward to you guys' input. But one of the things that's very different between those two virtualization, open source virtualization, is how QEMU is used. In KVM, it's kind of used fully. It's both as a control stack as an emulation layer. On Xen, it's only used as emulation layer. Now, why does this matter to me? So one of the things that Oracle, who I work for, is we're also a public cloud provider, and we're really worried about attacks. It's great we have customers, but at the same time, those customers can get hacked and they become evil customers. And when that happens, we really are not too happy about it. And there's multiple ways this can happen. There's the attacks through x86 opcodes, there's the hypercalls, the MSRs, there's a whole bunch of them, and there's also QEMU. This talk is more about QEMU, so let's just focus on that one. Now, if you actually look at the architecture of how QEMU is being used inside of both KVM and Xen, on the right side, we have, I'll try not to use the pointer. On the right side, we have how KVM. And you can see this giant, we have QEMU, and inside of that is where the guest is actually running. That is the memory of it. On the left side is how Xen is done. The memory is actually being controlled by Xen of it. And QEMU is on the side of it, and it just does emulation. To make that work, there's another path of it, which is the control stack. And the control stack, called libvirt or libxl, all manage the guest along with telling QEMU what to do. And alongside of that, there is also the kernel. The kernel has a lot of the backends. So on Xen, instead of having a virt.io, it's called Xen PV drivers. And most of the ones are in the kernel space. All right. Now, one thing that some people may not know is that you can also do something that's kind of tweezing apart all of the things. One of the ideas that Xen had was you want to separate as many components as possible, because then you can concentrate on the smaller ones and make sure they're as much secure as possible. And to make that happen, they realized, well, there's some components we just can't really do a good job of making sure that they're secure, valid, that we can certify. We can go through code by code and figure out, hey, is this really secure? So they came up with this idea of tweezing things apart even further. So one of the things is like, well, why don't we just put QEMU inside of a guest? You put a gel around it. If it breaks, well, it breaks. And if it does break, then you know something is wrong, and you might as well kill both guests. It's a great way of stopping attacks. Now, how does it actually work? So the QEMU part does the emulation, right? We have E1000. It ends up taking the packets from the guest, or the guest writes to it. And then on the other side, it has actually a PV driver. So it talks to the initial domain, the first Linux kernel, and which actually does send all the packets over the network. And it picks it up from the QEMU stub domain, which basically takes packets from the guest and then sends it over and tells the backend, hey, this is where you're supposed to go and pick it up. So the attack vector is actually, in this case, if a customer, evil customer, gets into the QEMU, they have to do attack through the PV ring. That's their attack vector. Now, in the past, there had been attacks, pretty cool ones actually. One of them was this GCC interesting optimization where it would pick up an index and then it would double fetch it again, and you would do a jump table, and it was a pretty neat attack, but fortunately it's all fixed. But past examples have shown that the neat thing about any PV protocol, virtio or Xen, is it's simple. I mean, it's there, but it doesn't have that many things, and it's pretty reliable. So there's a lot less chance of any attacks. Now, here's an example if you're using serial. I'm going to skip over it since we don't have that much time. As I said, there's a lot of slides, and I really recommend that you guys take a look at it afterwards and go through them in details. Now, what does all this mean? As I kind of referred to at the beginning, is you have a jail around it, meaning it's all kind of running inside of VMCS, so that if something does break, it's, you still have another way of, you don't have that many ways to get out of it. Now, this is, of course, not a talk about Xen, because on the slides it says KVM forum, so let's jump to KVM. How can we make something like this similar if we wanted to do it in KVM? Well, here's an example of how we can do it, and what I figured is, Mark has been actually looking at this in much more details, so I will jump over to him and let him focus on the core deep parts of this one. Oh, wait, sorry. Jumping a little bit ahead here. There's also the question, why would you actually want to do it? I mean, we have a whole bunch of pieces in QEMU already that try to secure things. You can do a lot with SC Linux. There's SecComp. There's also C-root jails. All of these things can do it. But as I said, one of the things that at least security people are really conscientious about is trying to erect barriers around pieces and seeing if those barriers are as much as possible audited, and then also the code that they trust really audit. And that's what we all want in a cloud environment. We want to make sure that we sleep at night without having to worry about exploits. All right, let's switch over.
Thank you. Shift F5, yeah. All right. So this is next. So yeah, I'm going to focus a bit more on QEMU. First of all, I must say this is a broad subject, as you can imagine. And we are going to focus perhaps a bit more on the device aspects, because when you think about multiprocess in QEMU, it's very generic. But I'm going through like many aspects of what you can do today with QEMU and multiprocess work on Link. And you might remember this talk 7 years ago, and I think that's one of the reasons why QEMU is designed this way. There is a lot of historical background, and I think the way the things are today is not necessarily the things have to be in the future. So, but you may just remember this talk has a similar title. It's just a bit funny. So I'm going to list a few facts of what QEMU is today. We are going to see what, in general, what is a device like in QEMU, and so what we need if we want to handle it out of process. And what exists today in QEMU, because I think many people don't realize what you can do already. So first of all, well, QEMU is one of the biggest binary on my laptop, and it's not just one binary, it's 10 binaries. And it's a very big binary, right? But Docker is beating us, so we are still not so bad. And it's also a lot of code, right? And nobody can really, yeah, it's a lot of code, right? We all agree on that. Whenever we need to do some refactoring, it's daunting. By comparison, the Linux kernel is 16 million lines, and we are about 1 million lines. And I think one of the reasons why there is like more and more projects using KVM without QEMU, it's because what you need is actually just a subset of that, right? I mean, you can run a Linux operating system very efficiently with KVM tool, and it's about 27,000 lines, so nothing compared to QEMU. And even if you want to, study or hack something, it's actually much faster and easier to do it with KVM tool, right? So it's a bit sad that QEMU doesn't offer this kind of flexibility. And I don't know if you know this project, but while I was working on the slide, because this is I was looking at so many things, and I discovered this project from Google, which actually use multiprocess for the device handling. So I encourage you to look at it, and it's written in Rust. And the whole code is about 30,000 lines, and it's amazing. So it has all the bindings for Rust. So actually, just the core of the code is probably 10,000 lines, or I don't know, because it even has to re-implement like Unix socket handling because Rust doesn't support certain things. So you can imagine. And it's not just the size of the binary, right? It's all the things we depend on. And yeah, I'm going to that after that. And so we can see the trend, it's not over. And we are writing this code in C. What could go wrong? Yeah, we have about 60 direct dependencies, and that total of indirect dependencies 160 almost, and there is probably more than that if you think about what can run dynamically. KVM tool only use 19, even with all the options on. So yeah, that's what I think. Yes, so this is like what was the goal 7 years ago, because QEMU was not, as far as I know, was not multi-threaded, sorry. So we have a lot of, the way the things are designed are, people were thinking mostly as a single thread. And the goal was to have a permissive thread and device thread. It's not exactly like that today, but we do a lot of things, right? And we managed to put certain things in different threads. So it's Paulo's talk, actually, from 4 years ago, this slide. And, well, correct me if this is wrong, but I think this is still, like the picture today, this is still the design mostly. So we managed to put some devices handling out of the main thread, basically. So we have kind of thread on device threads, let's say. Or even queue threads, we can do that, I think. But yeah, there is tons of things running in QEMU, right? And the idea is to try to put this apart and make QEMU code base smaller and safer and so on. So yeah, that's what ideally I think we should try to get to. Yeah. So, but this is the trouble, right? You get a lot of actually interaction between all these devices very quickly, and not just like the devices, but the helper thread and the helper processes. So yeah, this is an old debate actually. You may remember the kernel discussion about this monolithic versus microkernel with Linus and Tannenbaum, I think. And yeah, it's difficult to manage because we've got lots of processes to manage. Difficult to debug, obviously, for a developer. It's not just one process you can put under GDB. Difficult to test because if you have a combination of versions and so on, this is a lot of trouble. And some people are concerned about performance, and today, yeah, it's probably a concern in some cases. But why we want it? So Konrad listed already many reasons for the security. One of the reasons also, my motivation also is to have some modularity, especially if we have like different, if we have alternative to QEMU, they might implement the same thing again and again and again. And it would be interesting if we can share, like for example, one thing that is pretty complex is the virtio GPU, right? It's not a simple device. And I don't think people want to re-implement it for KVM tool or for cross-VM if they need to do accelerated rendering on Chromium. So it would be interesting if we manage to have common interfaces and we can share some project, some device implementation and what's not. And yeah, obviously we talked about that. Yeah. And I'm not going through that, but there is a lot of, let's say, new stuff in the kernel to isolate your processes and nifty stuff. And it's not easy. I mean, we use some of them with libvirt and so on, as we said, but because everything is on single binary, you have to be very permissible, right? We cannot, I cannot really decide what QEMU really needs. And if I implement the virtio GPU device, for example, I know what it needs. So it's much easier for me to set the rules for this device. And because I mentioned that in the abstract, yeah, I think it could help in some cases when you have long-running processes. You may have like memory trouble, and maybe if we put workload in different processes, it may help in some cases for memory. But I don't think it's a big issue for QEMU, but just because I thought about that. Yeah, so how do we do that? How do we, that's good, we have some time. No?
Yeah, we do.
there are a lot of strategies to do this multi-process thing. The obvious thing is we could keep a single binary, right? And we could just fork, we could fork, we could set up devices or the work in QEMU and then just fork it and jail it and what's not. And so this is one approach that actually CrossVM has taken so far. Maybe they will, if we manage to have something in common, that would be interesting that we share something. But for now, they do everything in this binary. They set up the device, and they set up some sockets for communication, and then the device goes in a jail. And that's much easier to test and so on than to code, actually. So you don't have to define a stable API interface and so on. The other solution would be to execute a different binary, right? And I mean, personally, that's what I would like to see. But it's much more difficult because you need to define these stable interfaces, right? And it's better if this interface supports various kind of devices. Well, there is some concerns about how to deal with all these processes. So some people, where should we do that? Like if I start today, if I want to have my emulation in a separate process, can I just, should I do it in QEMU? Like should I hardcode the path of the binary in QEMU and QEMU should execute this? Yeah, well, some people don't really like that. So we had like a contribution a few months ago, like people started to do that with the TPM, and we were not really happy about that, but it's very convenient at the same time, and we want to keep like developers happy where they want to just start QEMU command line, and if it uses multiple processes, then QEMU maybe should be able to do that, but to do this safely is not easy because QEMU is using a lot of memory, and it's multi-threaded, so there is some concern when you fork. And well, of course, security reason as well. And the funny fact that you might not realize, but actually Slurp, you can set up like an executable to handle a connection. So this is kind of funny fact that there is actually executable path in QEMU. I think most people disable that in production, right? But and also in migration, I don't know if we disable that, but you can set up an executable to handle the stream. So we are doing this today already, right? And perhaps libvirt would be a better fit to handle all these different kind of devices, and I think that's where we are heading to probably for the real world, right? For the real use cases. Yeah. So how what is a device like in QEMU? So this is 10,000 feet view. I have not like the low-level system experience. So as Paolo mentioned, I am like in the top committers, but I do a lot of cleanups, and I'm not specialized in one architecture or something. Well, I know mostly x86 and KVM, so I'm going to focus more about that, and I touch various devices, let's say. So the way I understand it, basically, you've got device description. So depending on the device kind, you need to describe it, and you need to register it on the bus, get addresses, you can contact it, and so on. And basically, it boils down to registering memory regions, in different address spaces, and then you receive events on those memory regions, read and write events, and so on. And your device can basically interrupt the CPU at some point. So there is various ways of doing that, but to simplify it, it's just like, let's say there is just an interrupt, so you can say, hey, take care of this device now. And at the same time, your device sometimes needs access to the memory of the system, but maybe not all the memory, so we've got IOMMU support for that. And sometimes, so this is pretty low level in general, but if you go a bit higher, like with USB, well, it's a bit different, right? It's a higher level of abstraction. And a device usually needs to manipulate to be introspectable, to be discoverable, let's say, and to interact with it. Sometimes you need to have some ACPI registration or tables that, depending on your device. And device tree is kind of similar. You need to describe where your device is located and so on. And a lot of details. And in QEMU, we use a mechanism for that to build this kind of description. We use firmware config, so devices interact with firmware config to describe themselves. And then in QEMU, we've got a lot of code to handle the device state and the migration. So this is something we have to take care, we have to think about if we do the device out of process. And a lot of, like, if you start doing things out of process, if your device accesses the memory directly, you need to track if it's writing memory. So we've got dirty memory, region tracking, and so on. And QEMU has a lot of ways to introspect what's going on. So if you do it out of process, then you will need to interact with this so you can still see what's running and tweak it. So in KVM in particular, the way it works, and in QEMU, a few people, well, not a lot of people actually realize that. I mean, most people in the room, I suppose, know that. But yeah, when you run a vCPU thread, you use KVM and you say, okay, run it, and whenever the CPU touches the device in this memory region we talked about, then you get an exit, and you know the reason why and the location and some details. And at this point in QEMU, we take this QEMU lock we talked about that still exists, and that's like the legacy. And so in general, that's a traditional device. It's kind of synchronous. This is my understanding. Feel free to correct me. And so we go and we look up the memory region, and we do the read-write operation in the device. And then if we need to interrupt the CPU, we've got this ioctl to send an interrupt. So if we do things out of process, actually KVM has a few facilities to let us do this job out of process. And the way it works today for the host user is through IO event FD. So this is very nice, and IRQFD. So I think I'm going into a bit more details after. So yeah, event FD, you register an address, a length, and the length is just like a word size kind of, it's not a range. And you set the FD to be woken up if the CPU writes to this location. But this is as far as I understand, this is not the same way as we have seen just before. This is kind of asynchronous, and it's only on write operation. So it doesn't map the legacy devices. So this is good for modern devices that's kind of asynchronous. And perhaps, if we want to implement legacy devices, we could extend this API somehow, make it a range API to cover more memory region, because we don't want to have tons of event FD. And then we could also try to make it synchronous, but I think this wouldn't fly. So in general, traditional devices, so we will need something, obviously, in QEMU without KVM. We will need to think about the interface to tell the process, okay, the CPU tried to read and write here and without using KVM. But well, with KVM, we could use this device concept. So in KVM, you can set up devices in the kernel, or even like a link your pass-through devices with KVM using this interface. And we could kind of extend this or create our own kind of device. And basically, the way I think about it, but this is just some thought and nothing we need to spend much more time to have a concrete proposal. But the way I think it could work is basically, if we need to handle things synchronously, we could the same way as event-FD work, we register a memory region. We say, okay, I'm interested in read or write operation. And we can set up an event-FD. And the thing is, so once you register this region, we would wait for the event. But the thing, what would happen is the CPU would have to stop, right? While the other process handle this. And we would need to think, like, do we want to have several like how do we handle the multi-threaded case? If we have multiple vCPU and they all access the same device, do we multiplex everything in the same thread or in the same handler? Is there something smarter we could do? And the way I think it could work is basically if we multithread things, it's a bit like AIO API in Linux. You could get all the events that happen in the various CPU and then write back what you need or send back what you need or what you did on those memory regions. So I think it could work this way, but maybe I probably need to spend some time if there is interest in this. And feel free to talk to me if you have some ideas. Apparently, some people have already suggested something similar in the past, but yeah, for migration, I'm going to skip perhaps, but the idea is how can we share the infrastructure in QEMU and how can we keep like the tools we have to analyze the migration. Trouble is various devices, they use different kind of, and TPM, for example, I think they specify how the migration is handled. I think they have some format for serialization, serializing the state of the TPM and sending it over actually for virtualization purposes, I think. Yeah, and today, with all the things I'm going to list, it doesn't really exist. Like, you cannot really migrate the external process. Or there is very few things, but it doesn't handle all the cases. So what can you do today? Obviously, you can run like the UI in a separate process, and I'm going to be a bit controversial about that. I'm going to suggest a few things. Block devices is one thing. So the block layer, you can actually run it in a different process in some ways. The USB, the smart card, the management interface from Intel, actually, the TPM recently, so we've got the TPM emulation in a separate process. The device I shouldn't talk about. And vhost-user, obviously, this is the most popular today. And I don't know why Paolo suggested I talk about VFIO MDev. I thought, okay, maybe there is something to say about it. So yes, so VNC, I think, and Spice, they allows you to run the UI in a separate process, right? And you can resume and so on. It's very convenient. They handle migration actually pretty well. And with Spice, there is some extension. It's not being used, but we can have like a monitor and virtual terminals. So what else do you need in QEMU, right? I mean, why don't we just start this process and just remove all the SDL and GTK code from QEMU, and it would be, 100,000 lines less in QEMU to bother, and all the audio stuff, for example. So this is just a suggestion, right? But I think it's worth to think about because there is a lot of duplication of effort. Similarly, no, it's just like some stuff you can do today. I don't know if it makes sense, but yeah, you can set up an NBD server and run your block your image in a separate process. So this remove a lot of work from the main QEMU binary. Perhaps this is good enough, like for desktop use cases and so on. Like if you are not into very performance-sensitive application, then maybe we could make this a bit more generic or used more often. And we can probably optimize it, actually. And this is just NBD, but actually with vhost-user block, you can do also certain things, right? So we could try to push a bit the block layer outside of the QEMU main binary. Similarly, they are all like the same kind of ideas. So actually, Spice developed this protocol that you can, pass through your USB device or redirect your USB device from your client. Well, the same protocol could be used to run USB emulation of devices outside of the main binary. I think at least that would be neat if someone like did this hack. You just use the same QEMU USB code and you try to interface it with USB radio. Smart card is similar. The Intel management interface, if you didn't realize, it's actually running it in a separate process. If you want to, I think even you have to. Personally, never really used this device, but yeah. And then more recently in the merge, I think last month, is the TPM emulation. And as you can see, all these cases, they have different command line interface. You need to set these devices differently. Like in the case of TPM, there is some, you cannot just start this binary like that. I mean, obviously, you need to start it before you tell QEMU to connect to it and so on. But you also need to set up like the state of the device with some commands. So there is some stuff, some preliminary work to do. And if you want to handle the migration, I don't know all the details yet. It's supposed to come soon, but it's the same. Like you have a separate file or directory that you need to take care, and it's probably the management layer that is going to take care about these details. The problem is if everybody, for all the devices, start to implement its own protocol like the TPM did, and they have their own way of handling setting up the device and tearing it down and so on, then it's going to be a lot of code doing kind of the same thing, and it's a bit sad. So in case of vhost, you know vhost to accelerate device handling on the kernel side. It's been modified to work also in user space by just using the same kind of protocol and making it over a socket, basically, and it's very successful. So we have seen a trend recently. It used to be like for DPDK and for packet switching stuff and so on, and mostly network stuff. Now we have SCSI handling and block coming. I've done GPU stuff. Input, I know crypto, there is some patch pending. So we've got a lot of devices that people want to start to run outside of the QEMU binary. And this is neat. I mean, you can use this protocol with the various implementation of vhost-user. If you've got, KVM tool could implement vhost-user fairly easily. So they could benefit all these devices quite quickly. Yeah, I'm not going into detail how vhost-user work, but basically the outside process get access to the memory of the guest and knows the location of the ring, and then it gets some file descriptor to get notified when it needs to handle the ring, or it can notify the CPU that it has done the work it needs to do. And we recently have IOMMU support. So, currently this is not very secure because this outside process can actually do anything it wants with this shared memory, with the memory of the guest. But there is hope that in the future we manage to isolate the memory, so you only get access to the memory you are allowed to get access to. And there is some tricks we could do with, for example, user fault. It's not, I discussed a bit with Andrea about it. It's not yet possible, but maybe in the future we could have like IOMMU support in user space, some kind of emulated IOMMU. So that's very interesting. And so I said, actually that's why I wanted to talk about multiprocess. That started like that. I wanted to run the GPU outside of QEMU because the GPU virtual actually, when you use 3D, you've got tons of things to take care about, and one of these, for example, is to compile your shader. So it may take minutes to compile, and if you do it while you take the lock that we talked about, basically you block QEMU for a minute, right? And so this is not really a good idea to run NGL, and GL is not really safe API either, and so it's better if we can run all the 3D stack outside of QEMU, and QEMU doesn't have to link with Mesa and so on. And so the way I suggested it, and as you can see, it's a bit like goes back to the discussion, like should QEMU handle the process and should it execute it itself? The way I implemented it in the RFC series is I create this object that fork and execute this binary. So we could have a restriction on where the binary is located and so on, signature and what's not if we need to. Yeah, and that's the way it works, and it gives you actually better performance, and yeah, it's more secure. I have to, like most devices, they will need to interact with the main QEMU binary or an external process. Like it would be nice if Spice or VNC server was running in a different process than QEMU. So you need to give some update of what's going on the display and so on, cursor and what's not. So we've got just a few commands for that added on top of vhost-user, and they could be handled by something different than QEMU. But today in my RFC, it's just the QEMU binary. Right, I already talked about that. And so the last one is the VFIO MDev. I was really wondering like what Paolo suggested with VFIO MDev. Like it's not really multi-process, right? It's for those who don't know, VFIO is done. It's the API in the kernel to do device pass-through. And recently, it has the mediated devices support. So with this new support, actually, the interesting thing is someone from NVIDIA implemented a serial device in kernel. And it's not a hardware device. It's just it's using the internal kernel structure and API to do the emulation. And I was thinking, well, this is actually interesting. This is all in software, right? So why don't we do the same thing in user space? We could reuse VFIO interface and implement the same device and perhaps many kind of devices with VFIO So I started this work, actually, I just started last week, and I started talking, and it's going to land sometime in the mailing list for discussion. But for example, some devices like the one I mentioned, IVSHMEM, we don't really like it in QEMU for some reason. Well, we could just create a VFIO implementation in user space, so we wouldn't have to bother about the IVSHMEM maintenance and so on in QEMU. This is just an example, right? I have nothing against IVSHMEM personally. So if we implement this VFIO interface, and it's very few changes in the QEMU code base because it's just the same API basically, just over a socket. There are tricks to do, obviously, to do memory handling and so on. And we need like the KVM interface I talked about, like to handle the memory region exit. So we will need these kind of things for various kind of devices. But for IVSHMEM, for example, it's fairly simple. We probably don't need that. So yeah, and basically I have a proof of concept, this serial device, this PCI serial device implemented as an external process using the VFIO interface. Yeah, so do you want to do the conclusion?
Yeah, sure. So as you know, there's a lot of things. Like there's a lot of things that we can do. There's a lot of outstanding issues that we have identified and we believe are going to make it hard to make it just right. And you know, there's definitely different ways of making it hard, and it's more of like how we can do it and which ones are more appropriate for certain things. But this is pretty exciting, I think. If you guys have any questions, please raise your hand. There's also time right afterwards because there's a coffee break, so we can also spend some time after that. But I see one hand up there.
So thanks a lot for the great presentation. So you were giving the GPU as an example, but I think that from the start you really had 3 different ways that splitting things could really help. One was basically reducing the amount of code. Then you said something about improved security and you know, being able to. And then there is the performance aspect. And so, in your opinion, which ones are going to really drive things? If you take the GPU as an example, do you think, for instance, the performance improvement that you're expecting are sustainable in the future, or is that just the current state that makes it so that it's higher performance now? And do you think, for instance, that security is going to be very important for GPU, and if so, why?
Yeah, I mean, in general, I think it's not really about the performance here. I mean, if we have performance issue, we solve it. We try to find solution already today. So it's not really about the performance. What we want is to not degrade the performance if we start doing things out of process. And I think with, you know, if you use modern interfaces like VirtIO, there is no reason that you get lower performance if you do it out of, there might be reasons depending on the use case. So it's also device per device. For example, the GPU, I don't expect a big change of difference because most of the time is spent actually doing stuff in the GPU or doing stuff in user space to handle all the commands and checking and compiling and so on. So I don't think it's it's not really a matter of performance. It's more about security and modularity.
Yeah, I mean, the security part is, if you isolated the process, one of the neat things is you can do better SC Linux policies, be more targeted, and say this process can only be certain things. So you can raise the SC Linux policy labels that we want to apply to that process, which should give you a better, well, it will give you a better idea of what it is and what it shouldn't be doing, which is really, that's kind of what we're striving. And furthermore, you know, by separating the code out, then you can also start just focusing entirely just on that for a security audit, which is good. Thank you.
I have a non-technical question about this change. This change introduce a standard API in between parts if we're going to use modular QEMU. In this case, those parts of QEMU cannot be obliged to use GNU public license. And this is a big change in the whole framework. Right now, we are all resize in the single address space, and GPL protects our work. With a modular change, we will honor closed source parts, which could create some unexpected complications for our work. That's the question.
Right, so it definitely, this is not a short, this is a long road. This project is not going to take, a week or a month. So there's paths to it, right? You can start making these components being more modularized where we can load them during load time. That's one way to start slowly tweeze out that namespace isolation. The API part, that's the tricky one that we honestly haven't figured completely out, because all the devices have some of their own features that they want to expose to the guest. At the same time, there's a lot of them. So to make a generic API for all of those, it gets really hard. And for the beginning, I think it's going to be more iterative development, or some design iterative development where we try to have an API that includes some of them, and then we expand and figure out what goes. As I said, this is not a short-term thing, so it's not going to be done in a year. It's going to take a couple of years, and surely enough, there will be issues along the way that we will have to revisit to make it just right. And that's what it is. Thank you. Yeah?
But this change creates a way for proprietary extensions, which is not very good.
It makes way for proprietary extensions, which is not very good. Okay. Yeah, I'm not too happy about that either. I completely agree that this could be used then for other open source or non-open source to use it. I don't really have a good answer to that, except, the idea isn't to make it an ABI. It's the idea to make an API so that it would be based on the version of QEMU. It's not like we're not going to try to keep it in strict control, but more of being fluid. So every release of QEMU may change it. So there is going to be breakage. And that question of proprietary products linking into it, I don't really have a good answer. Sorry. I mean, do you? Yeah. Sorry. All right. Well, I appreciate everybody. Now it's coffee time. Thank you very much, and enjoy the rest of the day.